Welcome to my YouTube channel, dear guys. Now, on my previous lecture, I have told about internal energy and Helmholtz free energy as thermodynamic potential. And now, in this lecture, I shall discuss about the rest. That is the third one. That is called enthalpy of a system. That is H equals to U plus PV. This is the internal energy and this is the work. And when you add this, there will be the total energy of a system. Okay, so enthalpy represents the total energy. Okay, enthalpy represents the total energy of the system. Okay, now this is the mathematical definition of enthalpy. So what will be my dH? My dH will be du plus pdv plus vdp. So du plus pdv means dq, which means again from second law TdS, plus vdp. Now suppose if you consider the process to be adiabatic isobaric, that is, think about adiabatic isobaric process. So in that particular case, dH becomes 0 and H tends to minimum. Okay, H tends to minimum. So under this condition, that is when the process is adiabatic isobaric, the enthalpy of a system tends to minimum. Okay, now what we get from this equation? From this equation we get del that is from equation 1 we get del H del S pressure constant, that is T, and from this equation del H del P S constant, what we get? That is V. Okay, this we get. Now since dH is a perfect differential, what we can write? Since dH is a perfect differential, we can write del 2H del S del P. This must be equal to del 2H del P del S. Okay, so we can write this term as del S of del S del H del P S. This is P, and this is equals to del P. We can write it del H del S P S. So what is this del H del P S? That is V. So we can write del V del S pressure constant. This equals to del T del P S constant. Okay. So again, starting from the concept of enthalpy, we will get another relation, that is TPS. This is equal to VSP. Okay. So previously, from internal energy I get a relation, from Helmholtz free energy we get another relation, from enthalpy we will get another relation. Okay, now this is the third Maxwell's relation. Okay, so this, starting from the concept of enthalpy, we will get the Maxwell's third relation. Now from this expression you can also say the physical significance of enthalpy. Okay, what is the physical significance of enthalpy of a system? That we can write by using this equation. Okay, so by using this equation, okay, this can represent, that is dq plus vdp. This can be written as, so if the pressure remains constant, then dH equals to dq. So at constant pressure the entire heat is used to increase the enthalpy of a system. Okay, so this is the physical. So kindly ignore the noise which is coming from outside. So if pressure remains constant, then dH equals to dq. So this is the physical significance of enthalpy. So at constant pressure, at constant pressure, the entire heat is used to increase the enthalpy of a system. For class 11 and or higher secondary students, this question is very important. What is the physical significance of enthalpy in thermodynamics? So you have to write it. At constant pressure, the entire heat is used to increase the enthalpy of a system. That is this. du plus pdv means dq, that is plus vdv. So if you make pressure constant, this term will be 0. So dA is equal to dq. Okay. So this is a brief description about enthalpy. Now let us move to the last thermodynamic potential, which is called Gibbs free energy. Let us move to the next thermodynamic potential, which is called the Gibbs potential. What is it? The mathematical formula of Gibbs potential is that H minus Ts. And what is H? More commonly we can write as this, U plus Pv minus Ts. So this is the mathematical formula of Gibbs free energy. So if you take derivative, so this will be what? Du plus pdv plus vdp minus tds minus sdt. So du plus pdv means dq, so dq means tds, so these three terms cancels. So vdp minus sdt. So clearly it is a thermodynamic potential that tends to minimum at constant pressure and temperature. Okay, at constant pressure and temperature, this thermodynamic potential tends to become minimum. So that is for isobaric isothermal process. Isobaric isothermal process, what happens? dg becomes 0. That's why g tends to minimum. Okay, g tends to minimum. Okay, so what you get from this equation, say this given m1, so you can get del g del p, temperature constant, that is dt 0, so this is v. So del g del t, pressure constant, this is what? Pressure constant means this term is 0, so it will be minus s. Okay, so it will be minus s. Del g del p, temperature constant, this is equal to v, and del g del t, pressure constant, this is equal to minus s. Okay, fine. So again we do as we did in previous cases, that these are perfect differentials. Okay, so apply the perfect differential condition. So since dg is perfect differential, dg is perfect differential, and here is a function of p and t. Okay, so we can write del 2g del p del t, del 2g del t del p. Okay, so what we can write? This we can write as del del p of del g del t p t, and that we can write del del t of del g del p t p. Fine. So what is it? Del g del t, p constant minus s. So minus s p t, this equals to v, that is del v del t, pressure constant. So simple these things. So you have to practice these things. Okay, these are pure mathematics, so you have to practice this. So mainly focus on these things that I taught. Okay, and make it a habit to practice these things regularly. Okay, so spt, you go horizontally, so there will be a minus sign, this vtp. Okay, so thus starting from the concept of thermodynamic potential, we arrive 4 Maxwell's relations. Okay, and we see that these terms are known as potentials. So why? U, F, H, G, these are called potentials. Why? Now let us come to that issue, why they are called potentials. So what you see in these lectures, that each of the variables or coordinates tends to become minimum at a particular condition. Say you can write this. So under adiabatic isochoric process, U tends to minimum, and you can say under adiabatic isobaric process, H tends to minimum, or you can say under isothermal isochoric process, F tends to minimum, and under isobaric isothermal process, G tends to minimum. So each of the variables will tend to acquire minimum condition under different conditions. Okay. So what happens in classical mechanics? That a system is in equilibrium when potential energy is minimum. We all know it. When potential energy is minimum, system is in stable equilibrium, and that's why you can say that water flows from higher level to lower level, or you can say current flows from higher potential to lower potential. That is the reason. Similarly, the behavior of these four functions, or say four coordinates, is exactly similar to uh, exactly similar in thermodynamics, as the behavior of potential energy is classical mechanics. So that's why they are called thermodynamic potentials, because what in classical mechanics, what happens in classical mechanics, the behavior of potential energy is same as that of, as the role played by these four quantities in thermodynamics. That's why they are called thermodynamic potentials. In classical mechanics, a system is in equilibrium when V is minimum. Similarly, these quantities attain minimum value under certain specified conditions. So the role of these four quantities in thermodynamics is same as the role played by potential energy in classical mechanics. So for this reason, okay, these four quantities are called thermodynamic potentials. Okay, so dear guys, this is all about, so we did two things in two lectures. At first lecture, I shall discuss the Maxwell's relation by simple algebraic treatment, and in this second lecture I shall discuss the Maxwell's relations can be obtained by using these potentials. Okay, you can do any of the methods you want, and if it is given a particular method in examination, then you have to do that particular method that is given in question. So you have to practice these both. Okay, so you have to know these two methods. Okay, so this is the case of thermodynamic relations. Okay, now let us move to another issue. Okay, let us move to another issue, which is called T and ds equations. This is another application. Okay, T and ds equations, that means this is another equation. So there are three T and ds equations in thermodynamics. T ds equation. So there are three TdS equations. Today I have to do the first one. So remind it, when you do the first TdS equation, you have to assume entropy as a function of volume and temperature. This you have to assume. If you assume other, then you will not obtain that the result. So remember, while doing the first TdS equation, you have to consider entropy as a function of volume and temperature. Okay, now since ds is a perfect differential, you can write it del S del V temperature constant dV plus del S del T volume constant dt. Now you have to multiply it by T. So T ds, I write this term as first, this, and T del S del V temperature constant dV. What is it? T del S means del Q del T volume constant, that is CV. CV dt plus, what is this? Del S del V temperature constant. So you can write del S del V temperature constant means del P del T volume constant. Del P del T volume constant. Okay. So this represents the first T and ds equation. So you have to consider the entropy as a function of volume and temperature. So find ds, so that will be this, multiply both sides by T, you get it, and rearrange it, you can write this term. Okay. Now you can also rearrange this, also you can express this by another form. So let's do that. What is the other form of first T and ds equation? Okay, what is the other form? We all know that alpha, that is what? Volume expansion coefficient, that you all know. What is volume expansion coefficient? Increase in volume per unit rise in temperature, keeping pressure remains constant. That is called volume expansion coefficient or volume expansivity. Volume expansivity. Okay. Increase in volume per unit rise in temperature, keeping pressure constant. And what is ET? That you also know, that you taught in that you teach in first law, that is isothermal elasticity. Okay. This is the isothermal elasticity, this is the stress term, and this is the strain term. So this is the isothermal elasticity. This represents the what? Isothermal elasticity. Now multiply these two terms. What do you get? Minus VV cancels. So del V del T pressure constant, del P del V temperature constant. So PSTV. So what will be VTP? My VTP will be minus SPT. So minus plus SPT. PVT. So del P constant, what you get? Del S del V temperature constant. And del S del V temperature constant means del P del T volume constant. Okay, fine. Alpha multiplied by ET means this. So after simplifying and using Maxwell's relation, you have to rearrange this. Okay, so thus we can see the first TDS equation can be written also in this form. How? That is TDS, this you can write as CVDT plus T del P del T volume constant dV. And what is del P del T volume constant? That is alpha ET into dV. So this is also the another form. This is also the another form of first TDS equation. Okay, so let's find. So today's lecture I discuss about Helmholtz free energy and enthalpy and also first TDS equation. Now in my next class I shall do the second and third TDS equations and other issues. Okay, and I also tell that you must listen all these lectures, because I will do a lot of mathematics in this chapter and it is a very lengthy chapter. Okay. So dear guys, if you don't subscribe my channel, then kindly subscribe it to get latest videos on physics. Okay, thank you.